All right, so let's work through a few more ray diagrams. So this is question 9 on the chapter 23 recitation. We have an object 5 centimeters away from a convex lens. So that is a lens that bulges out in the middle. It'll be a converging lens. Has a focal length of 11 centimeters. We're going to draw a principal ray diagram to scale with 3 principal rays that show the approximate image location. And then we'll check with the mirror and thin lens equation to make sure everything is drawn correctly. I always like to start with the equation so that I know how to lay everything out. So that's what I'm going to do here. So in 9, we have a converging lens. So the focal length of a converging lens is always going to be a positive number in the equation. So the focal length is the 11 centimeters. The object distance is 5 centimeters. And we need to calculate the image distance. So we'll use 1 over dO plus 1 over di is 1 over f. We need to solve for this. So I'll subtract 1 over dO on both sides. Now we'll get rid of this. It says 1 over di is 1 over f minus 1 over dO. And then I'm going to take the reciprocal of both sides, so both of them to the negative 1 power, to solve for di. And that gives me the di is 1 over f minus 1 over dO to the negative 1. So on my calculator, I'm going to do, the focal length is 11, so I'll do 1 over 11, but I'm actually going to just type 11 to the negative 1 because that's fewer issues can go wrong there. Minus 5 to the negative 1, so 5 to the negative 1. I'm going to push enter. And now I need to take the reciprocal of that. So I'll take 1 over that, like that. And I get negative 9.1. Negative 9.2 centimeters. This negative here tells me that I'm expecting a virtual image. For a lens, so let's draw a lens that looks kind of something like this. It's a converging lens that is convex. It bulges out in the middle. For a lens, rays are going to be coming from the left and traveling through the lens out to here. So a real image would be formed back behind the lens, but a virtual image is going to be formed over here. So I'm expecting my everything to be over here. So I want to be able to make sure that I can resolve 11 centimeters to the left of this lens because that's the focal length. I want to also be able to resolve 11 centimeters behind the lens. So we always want to be able to resolve both of the focal lengths of the lens, one on each side. I want to be able to resolve 5 centimeters on the left-hand side of the lens because that's where DO will be. I also want to be able to resolve negative 9 centimeters, so 9 centimeters over here. It's also a good idea to check the magnification so that we know how big this should be. So I'll say that the magnification is negative di over do. So that's negative of negative 9.2 over 5. The two negatives will cancel, and that's, we'll calculate it. 9.2 divided by 5, it's going to be about 2, a little bit less is 1.8. So my image is going to be almost 2 times as tall as my object. So I don't want to draw a super tall arrow to start off with because the image is going to be twice as big. And it's also a positive number, so that tells me that I expect it to be upright. So we'll go upright, larger image. Okay, so let's go ahead and draw a line through the center of the lens, and we'll also draw a line this way through the center of the lens. So we've drawn in our principal axes of the lens. And now I want to be able to draw 11 centimeters. It looks like maybe I'll do, this ruler that I'm using, it only has inches on it. It doesn't have centimeters in a way that's convenient for me to use. So I'm going to actually maybe make every half inch be 2 centimeters. So there's 2 centimeters, 4 centimeters, 6, 8, 10, 12, And that's probably all that I need, but I'll keep going for a little while since I have that space. So again, I'm measuring from the center of the lens, not from this arbitrary location where I drew my edge of my lens. And it doesn't matter what scale you are using as long as it's evenly marked. So if you're just marking lines on a piece of paper, you might not draw them evenly spaced. So find something, even if it's just a piece of paper with lines on it that you hold sideways, that should work just fine too. Or if, the like gold standard here would be that if you have any graph paper at home, but I don't, and I don't expect you to either. When you do take this on a test, I'm obviously going to let you do the same thing here. So, find a way that you're drawing things to scale that works. And if you're not sure if it's working, make sure that you're checking in with me before we go to take the test. And make sure that you got this. So this will be 4, 8, and 12. So I'm going to label F and DO. So the focal length is 11. And I'll put it on both sides. And I'm going to put an object at 5, and I'm not going to draw it too tall because I'm expecting somewhere around 9 there to be an arrow that's about twice as tall as this arrow. Okay, so let's draw our 3 rays. So the rules for the 3 rays are always the same. So the first one is in through F, out parallel. Second one is in parallel, out through F. And the third one is in through center. And for our lens, it doesn't bend. For a lens, this third one is the easiest one to draw, so it's always the one that I start with. So we're going to draw a ray that starts at the tip of the arrow, and it's going to travel straight through the center of our lens, just like that. And I'll draw my ray as going out like that. Now let's come up in through F and out parallel. So you notice that F, there is no F between the object and here. So instead of our in through F arrow starting at the object and going through F, it actually is going to start at F and go through the arrow. So we want to imagine a ray like this that seems as though it came from F. And then this ray, though it kind of seems like it started at F, but it actually starts at the tip of the arrow. And it follows this sort of a trajectory, and then that is going to bend and go out parallel. Okay, and now our third ray is going to be in parallel and out through F. So I want to draw a ray that comes in parallel to the center axis. And then it's going to bend and go out through F. Okay, and now I can see that my lens is never going to form a real image on this side, right? All of these rays are spreading out. But my converging lens is still converging. So can you look at these 3 rays and convince yourself that they're spreading out more here than they are here? My lens just isn't quite powerful enough to focus these into a real image. But all 3 of these outgoing rays, if you were an observer over here somewhere, all 3 of these outgoing rays maybe seem like they're coming from a spot that we can trace back. And that's what we're going to do. So I'm going to take all 3 of my outgoing rays and just trace them backwards. So there's that one. There's that one. There's that one. So I traced my 3 outgoing rays, and it seems as though all of these rays started from this spot. And I've drawn my ray diagram, and I see that I have an image right here. That's the location of the image. It's virtual, right? That's what I expected. It's magnified. The arrow is about twice as big as the image arrow is about twice as big as the object arrow. And it's also upright, which is also what I expected. Okay. Let's move on to the next one. So now I have an object placed 13 centimeters away from a concave lens. So this will be a lens that caves in the middle with a focal length of 11 centimeters. And we have the same question. So it's the same numbers, the same everything, except now we have a concave lens. So let's modify and redo this. So my focal length of a concave lens, so that's a lens that looks like this. So it'll be a diverging lens. It spreads out the rays. It's still 11 centimeters, but for the thin lens equation, we're going to put that in as a negative number. The object distance is still 5 centimeters. And we'll just redo the equation that we already solved, which was that the image distance is 1 over f minus 1 over do to the negative 1 power. So this is going to be negative 11 to the negative 1. Oops. Minus 5 to the negative 1. And now I'll push enter and take that whole thing to the negative 1 power. And so this gives me negative 3.4 centimeters. Let's also calculate the magnification. So m is negative di over do. So that will be negative di, so we'll call negative answer, divided by 5. And that is 0.669. There's no point in keeping more. Well, let's keep 2 sig figs since we had that in the problem. So we'll call this 0.69. There's no units on that, okay, because it's a unitless number. So this tells me that I have a smaller image, okay? So image is smaller. If this number was 1, then my image and my object would be the same size. If it's bigger than 1, then my image is bigger. If it's less than 1, then my object is bigger. It's also upright because it's a positive number. We can also tell right here from this negative number that we have a negative image distance, but we are also still expecting a virtual image. Okay, so again, all three of these, like my image and my object, are going to be on the left-hand side of the lens for the same reason that it was up here with the same problem, but with a different shaped lens. So let's get our same numbers on. Oh, but before we do that, right now the image is going to be at 3.4 centimeters and the object is not going to be quite as tall. So I'm going to kind of not have to resolve things as far away, but I think I will probably still just keep that scale the same as it was before. So I'll draw my center of my lens and go like that. Now we'll go 2, 4, 6 centimeters, 8 centimeters, 10 centimeters, and 12 centimeters. 2, 4, 6, 8, 10, and 12 centimeters. And now I'll put in my focal points here and here, and I'll draw my my object. I'm going to go ahead and draw my object fairly tall since I know that my image is going to be a little shorter. So my object is here at 5, and I'll draw it pretty tall so that when I get my image arrow, it's not just kind of a tiny, impossible to see thing. Okay, so let's follow the same 3 rules. So I always start with the third rule, in through the center without bending. So we will go like that. And now, since I know that I'm going to have a virtual image, I'm going to go ahead and save myself some time. And I'm going to trace back sort of what that ray looks like following a straight line while I've got my straight edge there. Okay, now we'll go in through F and out parallel. For a converging lens, my in through F is a little different. So So previously, my in through F was this one. So it seems like it comes from F, it goes to the object there. That's what you do for the converging lens. For the diverging lens, my in through F is not in through this F, but in through this F. So I want to imagine a ray that is leaving the tip of the arrow and it is on its way toward F. It will never hit F because it's going to bend when it gets to the lens. So my in through F looks like this. In through F, right? So it was sort of en route to F, and now it's going to bend and go out parallel. And now I'll go ahead and use my blue again to trace what that outgrowing ray looks like on this left-hand side of the lens as well. Okay, so I have two rays. They hit the lens and they spread out. And right here is where they cross. I was expecting them to be 3.4 centimeters away from the lens, and this is between 2 and 4, how I've drawn it here. I need to get my third ray on there, but this is looking good so far. Okay, so now let's do in parallel and out through F. And I'll do that one in pink. So in parallel. And now it's going to bend and go out through F. Now, we're not going to be going out through this F. If I went out through this F, let me just kind of faintly in pencil draw what that would look like. We can talk about why that's wrong. If I went out through this F, then you can see that actually my two outgoing rays would be crossing, which is not what I'm expecting, right? I need a virtual image, which means that I don't want these rays to ever be crossing. So if you're expecting a virtual image and you get rays that are crossing, then that's a big clue to you that you did something wrong. So our out through F ray is going to be out through this ray. So out through F looks like this. There's my out through F ray. So it's in parallel and it's out as though it came from this F all the way back here. And now I can trace back my three outgoing rays like this, and they all cross at this one spot right here, which is the location of my image. It's about 70% as tall as I expected. It's upright as I expected, and it's at about 3.5 centimeters, which is also what I expected. Let's do one more, which is an object 5 centimeters away from a concave lens with a focal length. Oh, that seems to be the exact same question that I already did. Let me check. Oh, all right. So you might have noticed that this number here that I just did was not 10, but 11. Sorry about that. The dangers of doing things digitally is you make a mistake and don't notice it until 10 minutes later. So everything that I did here was right, but this right here has, sorry about that, the object distance is 5 centimeters. So this is number 11. We still haven't done number 10, so let's go ahead and do number 10 next. Okay. So number 10 says that I have an object 13 centimeters away from a concave lens with a focal length of 11 centimeters. So now I have F is 11 centimeters. And it's a concave lens. So a concave lens always has a negative focal length. And The object distance is 13 centimeters. And we'll use the same equation that we had before to do 1 over negative 11 minus 1 over 13 to the negative 1. And when I do that, I get negative 6. And the magnification is negative di over do. And that magnification is positive 0.46. So let's draw our array diagram again. So this is going to be a virtual upright. It's virtual because this number is negative. The image distance is negative. It's upright because the magnification is positive, and smaller because the magnification is less than 1. So let's again draw our same lens. Get principal axes on. We'll go 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. And the focal lengths are at 11. I'll go ahead and draw my object. Oh, has to go all the way out to 13 centimeters. So I need one more marking here. And I'm going to draw it somewhat tall because it's only going to, my image will only be half as big. Okay, so now we draw the third ray first. So that's the one that goes in through the center without bending. And it looks like that. We'll draw the second ray, which is in through F and out parallel. My in through F would look like this. I'm tempted to go in through F. That would be the ray that is the in through F ray if this was a converging lens, that was a convex lens that bulged out in the middle. But that is not what the in through F ray looks like here. The in through F ray is an in toward this F over all the way over here. So in through F is in toward F, and now it bends and goes out parallel. So that's just like what we did with the previous ray diagram. And now our third ray is in parallel and out through F. And again, we don't want to draw it going out through this F. We want to draw it going out through the F behind it. Okay, so my three rays are the pink one, the dark pencil one, and the light pencil one. As they exit the lens, they're more spread out than they were when they entered. That's what a diverging lens does. It always spreads out the rays more. A single diverging lens will always form a virtual image because all it can do is spread the rays out. And now I'll trace back. It looks like this one I've already traced back. This one I've already traced back. This one here I haven't traced back. So let's take the outgoing ray and trace it backwards. And now I can see that all three of these cross right here. And I have an upright image. My arrow is right side up. It's smaller than the object, which I expected, and it's right at about 6 centimeters, which I also expected. All right, so I think between all the ray diagrams that we've done on this, you have an example of all of the ray diagrams that can appear on the homework. So good luck, and let me know if you have any questions.